Hello, my name is Linot, and I work under Mike Graham at the University of Wisconsin-Madison in the Department of Chemical and Biological Engineering. Today, my talk will be deep learning for recreating chaotic dynamics with a minimal representation. So the background is that many systems of practical interest, such as turbulence, have many degrees of freedom and are highly chaotic. So here to the right, I'm just showing you a video of what that might look like, where we visualize turbulence with lasers and smoke at an outreach event for kids. And so the question of this talk is, if given data that looks like this, how can we model this system from strictly the data? And more succinctly put, what we're doing is database reduced order modeling of complex chaotic systems. And so the problem with trying to do this type of modeling is that often these systems require high dimensional state information and finely spaced data for you to either run simulations or make models for them. And the solution that we're going to use to try and overcome this issue is the fact that oftentimes with systems like this, trajectories will land on some sort of finite dimensional manifold that's much lower than the state dimension that you're given. And what we're going to do is we're going to find an exact mapping onto the coordinates that parameterize this manifold, and then an evolution in this coordinate system. And so this video I'm showing you here at the bottom left is just illustrating this point where a bunch of trajectories that are off of this stable periodic orbit eventually land on it. And so if we want to do long time predictions, all we have to do is model this, the dynamics on this one-dimensional manifold in this case. But in our case, we're dealing with chaotic dynamics. And so the manifold will likely be much higher dimension than one-dimensional. And so here to the right, I'm just showing a caricature of what this looks like. What we'll be considering is a state U that is on some manifold M, which is embedded in some d-dimensional ambient space. And we'll be considering coordinates H that are in dm dimensions, which are the coordinates that parameterize this dm dimensional manifold. And d is going to be much greater than dm. And so the objective again is to find a mapping onto this manifold's coordinate systems chi, and a mapping back to the full space AIChE, along with the vector field on the manifold G. So here I'm just showing an example of what this might look like. Here I'm showing you the Archimedean spiral. And so what we're going to try and learn in this case would be chi, which maps us to a line, and then AIChE would map us back out to the spiral. And then for finding evolutions, what we're going to do is we're going to find evolutions then on this line, where what we're going to do is integrate forward G so that we can make predictions forward in time. And the way that we're going to approximate these three functions, chi, AIChE, and G, in this case is by using neural networks, which are parametric models that we train iteratively from data. So what sort of data are we going to need for learning the mappings to the manifold and for learning the evolution? In the case of learning the mapping to the manifold, all we're going to need is U at some time, and then we're going to send it through what's known as an autoencoder to then try and recreate U as the output. In the case of learning the evolution, we're going to use something called ODENet, and the input to this model will be H at some time, and we're going to then try and reconstruct H at some time tau units forward. Now, in order to update these neural networks, we need a loss function. In the case of learning the coordinates on the manifold, the loss is just going to be the difference between the state U and the state U after running it through chi and AIChE. In the case of learning the evolution, the loss that we're going to be minimizing is the difference between H at some given time ti plus tau and the integration of H at some ti integrated forward to ti plus tau with our neural network as the right-hand side. And so just to show this in a diagram, in the case of learning the coordinates, we're going to take some higher dimensional U, put it through chi to get a lower dimensional H, and then put it through chi hat to get some prediction U tilde, which is what the difference in the loss is here. And in the case of learning the evolution, we're going to be taking H and putting it through some ODE solver to reconstruct an H tilde, which is what we're trying to make the same as H at that time. And in both cases, we are going to learn the parameters for these networks by computing these losses with respect to the weights of the networks, and then using a gradient descent method to minimize the losses. And in both cases, we're going to do back propagation in order to calculate our gradients. In this case, we're going to be back propagating through the solver, but in this Chen et al. Paper, they also show how you can use an adjoint method to calculate this gradient. Okay, so now that I've laid out our framework, let's talk about the toy model we're going to be using. The model we're going to be using is the Kuramoto-Sivashinsky equation, which has chaotic dynamics and long-time solutions lie on a finite dimensional manifold. And here's the equation for the Kuramoto-Sivashinsky equation. We're going to be using periodic boundary conditions, and we're going to be in an ambient dimension of 64, which is our grid spacing. And so what I'm showing you here to the bottom left is the heat map is the function u versus space, and the x-axis is time. And so here I'm showing you what a signal at time 0 looks like. So this signal is if I were to take a slice here at time 0. And if I run this video here to the right forward in time, you'll see that this signal changes chaotically in time. And if I were to just look at the signal frozen at one of these points, it would be the same as a slice in this heat map. So now what we're going to do, again, is first we need to learn our mapping to the manifold coordinate systems. And so I'm going, in this plot, what I've shown is I took that data that I showed you in the previous slide for a domain size of 22. I took a very long time series of it, and I trained those neural networks to reconstruct the state U. And so what you're seeing in this figure is the loss that I showed you on the previous slide on some test data that the network had never seen versus the number of dimensions. And here in this orange line is a specific type of neural network that we describe in this paper. And what you can see is that at a dimension of 8, there's a large drop in the error. And it turns out that this large drop in the error actually coincides with the true dimension of the manifold, which has been shown by Ding et al. Using other methods too. And so now what I'm going to do is I'm going to take this neural network setup, this mapping onto the manifold that I've learned at a dimension of 8, because we know that that's the true dimension of the manifold. And now I'm going to learn the dynamics in that coordinate system. And the thing that I'm going to vary when I'm learning the dynamics in this coordinate system is the data spacing tau. And so first of all, what I'm showing you here is when I have data spaced apart 10 time units, and I trained both the mapping and ODENet to reconstruct dynamics. And so here at the top, I'm showing you a time series of data. And here on this next plot, what I did, which is shown here, is I took the initial state U, I put it through chi to give us our coordinates on the manifold. And then I used an ODE solver with our neural network representation of G to predict H at a number of different time points. And then I just used chi check to recreate U. And that's what you're seeing here with this trajectory. And what you can see is that qualitatively, both the data and the model agree very well. If you just track this red line, for example, they follow almost all the way across. And if we look at the difference, we can see that it's almost exactly the same for around 20 time units. And then there's some predictive capability for another 40 before it starts to diverge. And the Lyapunov time for this system is around 22 time units. So it's hard to expect that we would get predictive capabilities for much longer than a couple Lyapunov times. And so what I showed you in the previous slide was just a single example, but we should look at ensemble average quantities to get a better understanding of how well we're doing predictions. And so here what I'm showing you are the temporal autocorrelation and the average error. And so first of all, let's talk about this temporal autocorrelation. So on the y-axis is the autocorrelation, and on the x-axis is the time lag. And each of the lines are colored by the spacing of the data that I've used for training ODENet. And what you'll see is that the blue line here, which is the data, matches very well with our method of learning the coordinates and then training ODENet for 10 to 15 time units of data spacing. However, if instead of learning the right-hand side, I were to just learn discrete time maps with a neural network, those are the X's you see here. And for all of these data spacings, you can see that they don't do a very good job of reconstructing the temporal autocorrelation. Also, if we look at the average error, you can see that for something like 20 time units, the error is very low for regardless of the data spacing for learning ODENet. And again, for the discrete time maps, the error is much higher. It's not until around 80 time units that the trajectories have completely diverged. And so that's what it looks like when I have 10 to 15 time units of data spacing. But as soon as I go to 16 time units, what you'll see is that both the temporal autocorrelation and the average error do a very poor job of recreating these statistics. And so in order to address that, why that happens, or in order to address how far of a data spacing we can actually get, let's now look at the long time statistics. And so here is the statistic I'm going to be considering. This is the joint PDF of the first derivative versus the second derivative, where what I'm showing you here is the probability density for sampling any spatial and temporal data point and evolving a trajectory over 10,000 time units to get this plot. And so here, what I'm showing you is the relative error between the data and my reconstruction using our framework for different amounts of spacing of the data. And so what you'll see is when the spacing is around 10 time units, that the joint PDF for the model matches that of the data very well, except for some very low probability excursions. This is on a log scale. However, if I go up to 20 time units of data spacing, you can see that it does a very poor job of reconstructing this long time statistic. And what I'm also showing you on this figure are for domain sizes of 44 and 66. And what you'll see is that the joint PDF is recreated well at much lower time units here. However, what we should be looking at is actually the Lyapunov time, which is the characteristic time scale for chaotic systems like this. And what we see is when we collapse all of these lines onto Lyapunov time as the x-axis, that they all land on one another. And we get around 0.7 Lyapunov times where we do a good job of recreating the statistics for all of these domain sizes. And once again, if we look at the discrete time mapping, it does a poor job over this range. And so that's our method that we've used. And what I've shown you is that it can use a low dimensional state representation and sparse data and still get excellent prediction. Now, there's plenty of other methods to do things like this. Some of the more notable ones are reservoir networks and LSTM have both been used with the Kerr-Moto sufficiency equation to get excellent prediction. But in both these cases, you have a high dimensional state representation and they're non-Markovian because they use past information. Also, we've shown in previous works, and I've shown you here, that you can use discrete time mapping, but again, you can't get data that's as far spaced apart, and you have a fixed time step if you do this. And then the other work that's sort of like ours is there's this work where they used a multi-step method to approximate the right-hand side, but you need very closely spaced data in order to do this. And so our key results today have been that we found the coordinates on a finite dimensional manifold that the KSE dynamics lie on, and we were able to find the evolution of these coordinates just using sparsely spaced data. And more specifically, by finding the manifold coordinate system, we were able to look at when there was a large drop in the error to determine the dimension of the manifold. And then we were able to learn the dynamics for data spaced apart 0.7 Lyapunov times apart, which is very far. And so in the future, what we've been starting to work on is doing this with 2D flows like Kolmogorov flow, where we have some predictive capabilities, but we're still struggling with trying to figure out how to learn the mappings onto the manifold. And so thank you, that's my talk. If you have any questions, my meeting time is 8 to 9 Pacific time, Thursday, November 19th. And here's my email and also Mike's email. Thank you.